Hello friends, subscribers and new viewers of this channel, and welcome to FPGA tutorials. In this tutorial we explain how to control DC motors by using Verilog and Vivado. We explain how to control DC motors by generating pulse width modulation signals that control the rotation speed and by generating two digital signals that control the direction of rotation. Here's a brief demonstration of how to control the motor. I'm using these three switches over here to control the motor. To start the motor, I need to turn on the first switch. And as you can see over here, the motor starts. To turn off the motor, I will turn off the first switch. Let's turn on the motor. Now, the motor is rotating clockwise. If I want to change the direction of rotation, I need to press the second switch, and you can see that the motor rotates counterclockwise. To turn off the motor, I simply need to push back or turn off the first switch. Now let's turn on the motor again, and we can see that the motor rotates clockwise. And by pressing the second switch, you can change the angle, or actually you can change the direction of rotation. Next, the third switch is used to control the speed of rotation. Over here, I implemented a control algorithm that has two control modes. This is the slow rotation mode, and if I press the third switch, we can see that the motor rotates faster. We can change the rotation by using the second switch, and we can play around. You can see that everything reacts in real time. And then we can go back to the low speed mode by turning off the third switch. And that's it. In the sequel, we will briefly explain the experimental setup, and later on we will present a detailed wiring diagram. So let's start. The experimental setup consists of FPGA. We are using Nexys A7 100T FPGA. Then it consists of a low-cost DC motor. Later on I will show the specifications of this motor. Then it consists of this low-cost motor driver. Also, later on, I will show all the specs of this motor driver. Then over here, we have an oscilloscope. This oscilloscope shows the pulse width modulation signals generated by FPGA. We control the motor by using these pulse width modulation signals. And finally, we have the power supply over here. The motor direction of rotation and speed of rotation are controlled by using this PMOD port. In fact, we are using these three pins over here to control both the speed of rotation and the direction of rotation. These pins are attached through a breadboard and these wires to the motor driver. On one side, the motor driver receives control signals for direction of rotation and speed of rotation. On another side, that is over here, the motor receives the power and the ground from the power supply, and finally the third connector of the motor driver is connected to the actual motor. The oscilloscope probe is attached to the pulse width modulation pin and the ground of the FPGA, and consequently over here on the oscilloscope screen you can see the generated pulse width modulation signals that are used to control the speed of rotation of the motor. Let's see what happens when I turn on this switch for increasing the speed of rotation. You can see that the pulse width increases, and in this way, that is by modulating the pulse width, we can control the speed of rotation. So let's go back to the low mode or low speed mode, and again if I turn on this pin, you can see what happens. And let me change the scale over here such that you can nicely see the pulses. And let me go back to the original. Okay, let's start with explanations and with implementation. In this tutorial, we are using Nexys A7 100T FPGA. This is a very popular FPGA that is often used in electrical and computer engineering programs in the US and Europe. However, everything explained in this tutorial can easily be used in the case of other FPGAs. The Verilog code will be the same. However, you might have to implement a different constraint file, and I will explain this later on. But before I start with the explanation, here is a very important copyright notice. This video lesson, developed code files and documents should not be copied, redistributed, or posted on public or private websites, public or private code repositories, or social media platforms. This lesson and all the provided study materials are strictly for personal use. Without the permission of the author, this lesson and the provided material should not be used for commercial purposes and for training of engineers working in companies. Then, this lesson and the provided material should not be used as lecture materials on online learning platforms and in official university courses. Finally, this lesson and the provided material should not be used to train an AI algorithm or a large language model. Here is the top view of the experimental setup. Here is our FPGA. Here is the P-mode port that's used to control the motor. Here is the breadboard. Here is the motor driver. It's a low-cost L298N motor driver. And here's the motor. Here's the motor number, JGB37520, 12 volt. Here's an explanation on how to wire the motor driver with the motor power supply and with the FPGA P-mode ports. The motor driver has 3 ports. This is the first one, this is the second one, and this is the third one. This pin of the first port should be connected to the power supply voltage. This pin over here should be grounded. That is, this ground should come from power supply, and this ground at the same time should be the ground of the FPGA, such that we have the common ground. This port over here, consisting of these 3 pins, we are only using these 3 pins, are used to control both the motor speed as well as the motor direction of rotation. We will explain the purpose of these pins and how to connect them to the FPGA P-mode ports later on. Then we have this third port consisting of 2 pins. The motor has 2 wires. Usually it has a red wire and a black wire. It really doesn't matter how you connect motor to these pins, the order of wires doesn't matter. However, the motor wires should go here. Okay, next, let's explain the purpose of these pins and how to connect them to the P-mode ports. First of all, to repeat, we are using the P-mode port over here. This P-mode port is the port that's closest to the UART to USB connector. That is closest to this port over here. So let's explain. First of all, if you zoom in, you will see that there are 3 pins on the motor driver. They are IN 3, IN 4, and ENB. Of course, there are 3 additional pins, however, we don't use them. In fact, this motor driver can control 2 motors. We are only using the right pins. Let's explain. First of all, the IN3 pin of the motor driver should be connected to P-mode pin 1, and the P-mode pin 1 is shown over here. Namely, this is the cross-section of this P-mode port over here. And the pin 1 is this pin over here, and you can see this orange wire going from pin 1 to the breadboard, and then from here it goes to IN3. If you open the FPGA board schematics, you will see that the name of pin 1 is actually H4. And this name is very important since we will need to enter this name in a constraint file that we will write later on. Okay, next we have the pin IN4 on our motor driver, and this pin should be connected to PMOD pin number 2. And here's the pin 2 of our PMOD. Now if we go back and we look at this photo over here, the pin 2 is represented by this dark magenta line. And you can see it goes here, then it goes to IN4. Okay. The internal name of this pin 2 is H1, and consequently we will need this name in our constraint file. Then we have the ENB pin of the motor driver, and this pin should be connected to PMOD pin 3. That is to this pin over here. Now if you look at this photo, you can see this yellow line over here. That is the yellow wire. It goes here, and then it goes to ENB. The internal name of pin 3 is actually G1, and we will need this name in our constraint file. Next, let's explain the purpose of these pins. The pins IN3 and IN4 are used to start or turn off the motor and to control the motor direction of rotation. On the other hand, the pin ENB is the pulse width modulation pin. That is, we will send the pulse width modulation signals to this pin over here. And here is the explanation of how to control the motor. The motor is off in two cases, and here's the first case. In the first case, we send to pin IN3 and IN4 low voltages at the same time. And this will stop the motor. Similarly, if we send to both pins IN3 and IN4 high voltages, then the motor will be off. Then, to turn on the motor and to produce the clockwise rotation, we need to send to the pin IN3 high voltage and to the pin IN4 low voltage. On the other hand, to turn the motor on and to produce counterclockwise rotation, to the pin IN3 we need to send the low voltage, and to the pin IN4 we need to send high voltage. And that's how we control motors. Now, what is very important to keep in mind over here? We need to remember these pin names. Pin 1 is H4, pin 2 is H1, and pin 3 is G1. Let's continue with Verilog implementation. Okay, let's start from scratch. Click on Start and search for Vivado. As you can see over here, I'm using Vivado 2024.1. However, you can also use even a newer or an older version of Vivado. It really doesn't matter. The Verilog implementation will stay the same. So let's open Vivado and let's be patient. Usually it takes maybe 10 to 15 seconds to start Vivado, depending on how fast is your computer. And you can see AMD purchased Xilinx. So let's create a project. Let's click on Next. Let's click on Next. Let's keep the default options. Let's click on Next. And over here we need to select the board. So click on the board and search for your board. In my case, it's Nexys A7 100T. Here is one very important thing to keep in mind. The first time you start Vivado, you might not see any board over here. Consequently, you need to click on Refresh. After you do that, you need to download your board files. To do that, find your board and simply click here to download the files and to install them. After you install them, you will see this minus sign. This means that your board is installed and you can use it. Over here, my board is already installed, so I will click on Next and I will click on Finish. Here we are. The first step is to create a constraint file. The purpose of the constraint file is to tell to Verilog and to Vivado how these physical pins on our FPGA are connected to the variables in our Verilog code. So let's do that. First of all, over here, you need to click on constraint, then click on plus, make sure that add or create constraint is selected, then click on next, over here create file, and let's call the file as constraint, and click on OK. Then click on finish, and now if you expand this folder, you will see this file constraint.xtc. So let's open this file, and over here to save time, I will simply paste the content of the file. Here it is. And let's explain this file line by line. Whenever you want to implement a design in FPGA, you need to define a clock. And that's precisely what's happening over here. First of all, I looked into my board schematics and I found that the clock is connected to the pin E3 on my board. This is an internal pin that's actually not external PMOD pin. That is, the first step, open your board schematics and search for clock and find the hardware pin to which the clock is attached. The clock frequency in my case is 100 megahertz, and we will use this information later on. Now, you type set property package pin name, and over here we need to refer to a variable that's actually declared later on in the Verilog module that we will write. For the time being, I'm just typing here CLK, which is an abbreviation for clock. That is, CLK is actually a port that will be declared later on in the Verilog module that I will write. However, we need to use it over here, since with this statement we are saying the following: constrain this port clock to pin E3 to which our hardware clock is attached. Good. Next we have this statement. This statement formally creates our clock. The name of the clock will be system clock. However, over here you can use any other name, and over here we need to define the period of our clock. By looking at the board schematics, I found that the clock frequency is 100 megahertz, and this corresponds to 10 nanoseconds. Consequently, over here I'm writing 10, which corresponds to frequency of my hardware clock. Next, we need to define the waveform of our clock. What are these two numbers? First of all, this 0 means that the rising edge of our clock should happen at 0. That is, at 0 nanoseconds inside of a period of a clock. Then, the second number 5 means that the fall edge should happen at 5 nanoseconds. And this part is the same. We are constraining the clock to the port called CLK. And this third line is the classic line. Here we are defining the I/O standard. We are using LVC MOS33, and again we are constraining this to the port CLK. Good. Now we have defined clock. The next step is to constrain the motor pins as well as the switches. So let's go back and let's look at this photo over here. First of all, we need to constrain these 3 pins. And then we need to constrain these 3 switches. Again, by looking at this explanation over here, we can see that we need to constrain pin H4, pin H1, and pin G1. So let's do that. We do it like this. First of all, let's do it for IN3. IN3, that is this pin of the motor driver, should be connected to the pin H4. Consequently, we type set property, and here, instead of using this type of statement and this type of statement, I can simply compress them in a dictionary, and I can type package pin, then I specify the pin H4, that is this pin over here. Then I'm specifying IO standard LVC MOS33. And then here is a very important part. I'm constraining this pin, or better to say, I'm constraining a port of a Verilog module that I will write later on to this pin. The name of the Verilog port is motor, and in fact this will be a 3-bit port. Namely, for every pin over here, I will assign a bit. And these bits will be motor 0 for this one, motor 1 for this one, and motor 2 for this one. And that's precisely what's written over here. Motor 0, that is port 0 of motor, and motor is the port name that will be declared later on in the module, is constrained to H4. Then I do the same for the pin H1, that is for the pin 2, for this pin. I'm simply constraining this pin to motor 1. And finally, I'm doing this for the third pin, whose name is G1, and I'm constraining it to motor 2. Consequently, by sending 0 or 1 bit to motor 0, motor 1, and motor 2, I can control ion 3, ion 4, and E and B by controlling the pins H4, H1, and G1, and that's the main idea. Next, we need to do the similar thing for our switches, that is for switch 1, switch 2, and switch 3. Consequently, over here, we are constraining the corresponding hardware pins to this port called switch. Again, this port switch will be formally defined in the Verilog module that we will define later on. Since numbering in Verilog starts from 0, this is actually switch 1, this is switch 2, and this is switch 3. That is these switches over here, switch 1, switch 2, and switch 3. Now, by looking at the board schematics, I found that switch 1 over here is attached to the pin called J15. Similarly, switch 2 is attached to the pin L16, and switch 3 is attached to the pin M13. And these three statements simply constrain the switch port to the corresponding pins. And that's it. This is our constraint file. The next step is to create a Verilog module that implements our design and our algorithm. Consequently, let's expand this part. Click on Design Sources, then click on plus. Click on Add or Create Design Sources, click on Next, and over here click on Create File. Let's call the file as main_module. And here it is. Click on OK and click on Finish. Then click on OK once more and click on Yes. Then after some time, if you expand Design Sources folder, you will see main module. So let's double click on the main module, and over here let's erase everything and let's paste the content of the module. Here it is. And let's explain this file line by line. First, we need to define time units or the time scale. In our case, the time scale is 1 nanosecond. Next, we need to define our module. The module has two inputs. The inputs are CLK, which is an abbreviation for clock, and switch. First of all, let's explain CLK. CLK is actually a clock. Well, if you go back to the constraint file, you will see that CLK port is constrained to the physical pin E3 to which our clock is attached. Consequently, by using clock, we can use the physical clock in our Verilog module. Then we have this input port called switch. It is 3-bit wide. Consequently, if we go back to the constraint file, we can see how the switch bits of the switch port are constrained. They are actually constrained to the physical switches of our board. That is, switch 0 is here, switch 1 is here, and switch 2 is here. Again, keep in mind that Verilog starts counting from switch 0. That is, if for example a user presses over here this first switch, the second one keeps off, and the third one he or she keeps off, then over here we will see for the first bit 1, and the second bit will be 0, and the third bit will be 0. Okay, let's continue. Then we have a single output port. It's called motor, and this output port is used to control the motor driver. If we go back to the constraint file, we can see how the bits of the motor port are being constrained. They're constrained to the pins H4, H1, and G1. That is, motor 0, that is the first bit of motor port, is used to control ion 3. Motor 1, that is the second bit of the motor, is used to control ion 4, and motor 2 is used to control E and B. Good. Next, we declare a register called control. This is a 3-bit wide register, and we initialize its value, 0, 0, and 0. The first bit of the control is used to control ion 3. The second bit of control is used to control ion 4, and the third bit of control is used to set the speed. If we set the third bit of control to be equal to 0, this means low speed, and if we set the third bit of control to be equal to 1, this means high speed, and later on we will implement this logic. Next, we declare 3 integers, or better to say 4 integers, that are used to control the frequency and the pulse width of the pulse width modulation signal. We are using this integer to control the frequency of the pulse width modulation signal, and currently it's written 1 million. However, the units of period length are clock cycles. Consequently, you need to multiply this by the period of the clock, and the period of the clock is 10. Consequently, over here you obtain 10 million nanoseconds. 10 million nanoseconds corresponds to 10 milliseconds, and this corresponds to the frequency of the pulse width modulation signal of 100 Hz. Of course, you can change this value and you can experiment and see what is the best frequency of the pulse width modulation signal. Next, we declare 3 integers that are used to control the pulse width. Pulse length 1 corresponds to the low speed, and you can see that it's equal to 200,000. Consequently, the duty cycle is 200,000 divided by million. That's 20% of duty cycle, and this is the low speed. Over here we have high speed. For that purpose we are using the pulse length 2. Consequently, if we divide 900,000 by million, we get the pulse width of 90%. And this third integer over here is the final value. Depending on what switches are pressed, that is, depending on the switch value, we are going to either select pulse length 1 or pulse length 2, and we are going to store them in pulse length. Okay, next, we declare an integer called counter, and this integer is used to create the pulse width modulation signal. The pulse width modulation signal is actually implicitly created over here. Actually, we are using this part, and There is one part later on that's actually used to assign the values. However, this part is used to actually define precisely the counter. We want the counter to go from 0 until the total length of our pulse width modulation signal. That is, we want counter to go from 0 until one period of pulse width modulation signal. So how do we do that? Well, since our design is attached to the clock, we can use the clock. This always statement, or better to say the block under the always statement, starting from begin and ending at end, is executed at every positive edge at clock. So what happens? Inside, if positive edge of clock is detected, or better to say if a rising edge of the clock is detected, and if counter value is smaller than the period length, that is smaller than 1 million, we are simply incrementing the counter. And we are doing that, we are incrementing the counter until the counter becomes equal to the period length, that is when it becomes equal to the 1 million value, then we simply reset the counter. And in this way, we define the counter that goes from 0 until the total period of the pulse width modulation signal. Then, once again, a new rising edge of clock arrives, we reset the counter, and we keep on counting again. And that's the main principle. To be more precise, this always statement is used to count the positive edges of clock. In a single period of the pulse width modulation signal, we need to have 1 million of positive edges of clock. Later on, we are going to use the counter, and we are going to compare the value of the counter with pulse length 1 or pulse length 2 to define the high and low values inside of our pulse width modulation signal. The next step is to resolve the user input, namely by pressing the switches over here. For example, by specifying 1, 1, 0, the user actually fills in the bits of our switch port. Then over here, if any of the bits change, that is, if user either presses on or off any of the switches, this block under this always statement will be executed. That is the block starting from 32 until 60. So what's happening over here? We're simply defining a case statement. Inside, we are analyzing switch. So what are the combinations? First of all, if the user keeps the first switch off, this means that the motor should be off. And let's resolve this case. We simply type case Z and we analyze switch. If the first bit of switch is actually 0, this means the motor should be off. And then if we go back and if you look at our table, the motor is off if both IN3 and IN4 are low. Consequently, over here we set control. The first two bits should be 0 and the third one bit is also 0. However, you can also specify 1 over here. These question marks mean the following. Namely, they actually cover the 4 cases. Since user can enter, for example, 110, 100, 000, etc. And we have 4 combinations. Consequently, with the single case over here, we cover all 4 combinations. The main thing that the bit 1 is 0. Next, if the user presses the first switch, the motor should start. And let's analyze this case. That is, if the user presses the first switch and both second and third switch are off, this means switch 1 is pressed, this means start the motor, 0 over here means that the motor should move in the clockwise direction, and over here the third 0 or the third bit, that is the third switch off, means that we are moving with the low speed, and consequently we set control to be 0 for the speed and 0, 1 for the 2 pins. Consequently over here we are setting IN3 to high and IN4, no, actually we are setting IN3 to high and IN4 to low. Consequently, we have this code over here, B001. Then, if the user wants to move with faster speed, he or she will press the third switch. It will keep the second switch off and the first switch will be on. Consequently, the control should be this. We are still moving in the clockwise direction, only the speed is faster. Then, if the user wants to move in the counterclockwise direction over here, then we simply say the following. Actually, this is the counterclockwise case. So let's analyze this case. So let's repeat. If the user wants to move in the counterclockwise, he or she will set the following. The third switch will be off. Then the second switch will be on. This means that we want to move in the counterclockwise direction, and the first switch is 1, which means that the motor should stay on. And consequently the combination is 0, 1, 0. This means the following. If you look here, IN3 is low and IN4 is high, and that's precisely what is encoded over here. Then we have this case. If we want to move in the counterclockwise direction with high speed, we simply have this case. All 3 switches are pressed, and this is the code. This is the speed, then this is IN4, and this is IN3, and that's it. And any default case will turn off the motor. And that's it. Simple as that. Over here, we adjust the speed. Namely, we analyze the third bit of control. If the third bit is 0, we set the pulse length to be pulse length 1, which corresponds to the low speed. Otherwise, the pulse length is equal to the pulse length 2, which corresponds to high speed. Simple as that. And finally, what do we do over here? We simply assign the values to the output port called motor. And looking again over here, we can see where the ports or the bits of motor are attached. They're attached to H4, H1, and G1. That is, they're attached over here to IN3, IN4, and ENB. So what do we say? Let's see. We simply assign control 0 to IN3. We assign control 1 to IN4. And over here, we choose the value of the pulse width modulation signal. The value can be 0 or 1, depending where the counter is relative to the pulse length. Here, the pulse length has specific value, can either have 2000 or actually 200,000 or 900,000. Consequently, if the pulse is smaller than, or better to say, if the counter is smaller than the pulse length, this means send high. And you can see it over here. This is the value. Otherwise, if counter is larger than the pulse length, then send 0. And that's it. In that way, we are modulating the speed of our motor. And that's it. We can see that the code has literally maybe 55 lines if we compress everything. Okay, the next step is to upload the code. To upload the code, first of all, you need to run the synthesis. So let's do that. Click OK, and let's start the synthesis. This process might take. Then the next step is to run the implementation. You can either click on OK over here after selecting Run Implementation, or you can click here. Let's click OK, and let's click OK. Again, the implementation step might take a while, maybe even 1 minute. So let's be patient. The next step is to generate the bit stream. You can simply click over here and click OK, or you can click over here. Let's follow the first option, click over here and click OK, and click OK to generate the bit stream. And again, let's be patient. This process might take even 10 to 30 seconds, depending on how fast is your computer. Then meanwhile, attach your FPGA to the USB port of your computer, and then after this process completes, we will be able to upload our code. So let's wait until everything is completed. It shouldn't take too long. Verilog programming is actually very nice. However, you have to be careful, since way how Verilog works is a little bit different from C or C++. Okay, next let's click on cancel, then let's click on open hardware manager, then click on open target and click on auto connect. And this should open your port to your FPGA. And the next step is to program our FPGA. Simply expand this menu over here, click on the chip, do the right click and click on program device and click OK and program. And this should upload the code. Okay, now the code is uploaded and you can test your design. In the background you can see or you can hear how I'm pressing the switch. Or you can watch the beginning of this tutorial to learn the combinations once again. Okay, that's all for today and thanks for watching.